Hi, my name is Paige Allen, and today I will be talking about Physics 2211 Lab 1 called Constant Velocity. Here's a short agenda of today. There's 5 primarily categories that we will be talking about, so let's get started. The purpose of the lab was to observe an object that wasn't changing direction at its constant speed and compare that to a predicted computational model of constant velocity. For our observed position, we used an app called Tracker. For the predicted position model, we used a website Java program called GlowScript in order to get our data. The object that was observed was a roll of tape. Before we can even get started on the procedure, I think it's important to mention Newton's second law and momentum. If we are considering constant velocity, there should be no acceleration. Therefore, F net would be equal to 0. And when you plug that into the impulse momentum equation, considering that the mass remains constant, you will notice that F net over times delta t cancels, and therefore the final velocity should be equal to the initial velocity. Putting that into the update position formula, you will notice that the change of position should be the same constant velocity over time, which means there's a constant change of position, shown on the right-hand side. Velocity remains a straight horizontal line, indicating that there is no change in velocity. However, for the position time equation, you will notice that it is also linear, reflecting this, that it is constantly changing at the same rate. So for our observed data, we recorded a video of tape rolling in a straight line with no other force acting on it, other than when we pushed it. Imported that video into Tracker and aligned the axes and tracked the ball's position frame by frame, indicated by all the little red dots that you see on that tape in the photo. Then we viewed that data and copied it into Excel sheet to create a side-by-side comparison graph. For the computational data, we copied a code given into GlowScript, and we changed some parameters based on what we found in the observed data. So on the right-hand side, you actually see this is the final graph that came out when it was run, and you will see that the visual representation is also there, the ball moving towards the left. Here are some of the major changes that we've made, but I think the main ones to point out is that the ball's position was that very initial position that we saw, which was at a time of 3.33 times 10 to the negative second, which would be 1.18 times 10 to the negative second. The velocity, therefore, was the next nearest time frame, and we had divided that position on the right-hand side, divided by that time change on the left-hand side, which was put into an Excel sheet. The velocity, therefore, was also reflected by line 60, that change, based on the velocity equation that we noted, which should be equal to the same as its initial velocity. And the ball's position should be that constant velocity times time plus the ball's initial position. So here's the graph that came out, and you will notice that they look very identical in terms of slope. However, the tracker data seems to taper off at a position before the computational data, and this could be because of a few different errors. So the tape also experiences frictional force and air force, which is not considered in the computational model, which does not balance the applied force that we had put on it, resulting in non-constant velocity, with that slight bowing. So for also, the position tracking was done by hand, and there could have been a slight margin of error when we've tried to find the center of the tape, which also led to a bowing. Then also, when we started the recording, depending on where we started it, there could have been a significant velocity change, such as soon as we pushed it, or while we watched the tape starting to finally taper off. Some concept questions to consider that were given in this lab was what happens if the axis orientation is changed. So the numerical values or the magnitude remains the same, but the graph would likely flip from positive to negative, which is shown in that position versus time equation, as well as the velocity versus time. As you can see, the values would change signs from either positive or negative. Whether or not you can determine the forces being added depends on the scenario observed. Regardless of the forces, one condition would have to remain true, that the forces are balanced in both the x and y directions when you're considering the computational model. But for a typical case, you'll see applied force, frictional force, gravity, and normal force, with the y-axis being balanced, and then the x-axis is applied force is equal to the frictional force. The only problem with that is that we don't consider air resistance or other forms of resistance typically.